There is a machine, still moving, that has already stood in front of every kind of world this solar system has to offer. Jupiter's cloud tops in 1979, Saturn's rings in 1981, the pale disk of Uranus in 1986, the deep cobalt of Neptune in 1989, one spacecraft, all four giants, riding an alignment of planets that lines up roughly once every 176 years. By the time it finished, something built on Earth had reached every planet from Mercury to Neptune. That sounds like a schedule. If hardware already made the trip, a person following the same route sounds like the next chapter. Bigger rockets, more patience, more money. That reading survives almost the entire length of this story. Then it runs into a fact that does not care how reasonable it sounded. A spacecraft and a human body are not solving the same problem when they arrive somewhere. One only has to keep transmitting. The other has to survive the trip, survive the arrival, and, in most tellings of visit, survive the idea of coming home. Not every world closes for the same reason. Some close because of distance alone. Some close because there is nothing under the clouds to stand on. By the end, spacecraft already visited, every planet will not mean what it seemed to mean at the start. Let's begin. Start with the plainest version of the claim, because it happens to be true. Every planet in this solar system has already been visited by something built on Earth. The full list, world by world, hides more variation than the single word visited ever lets on. None of this happened at once, and none of it happened easily. The earliest interplanetary missions were built and launched inside a single decade. In a rush of competing national programs racing to reach anywhere beyond Earth's own orbit first, at a moment when engineers were still discovering, mission by mission, which parts of the plan would actually survive contact with real space rather than a drawing board. Cameras jammed, radios failed, entire spacecraft went silent within minutes of the moments they were built for, and were quietly written down as lessons rather than successes. The complete list of every planet visited that follows is not a single triumphant campaign. It is the surviving half of a much longer list that also includes everything that never made it. Mercury first felt a human-made shadow in the mid-1970 seconds, when a spacecraft threaded a narrow window past the sun's glare to photograph a surface no telescope on Earth could resolve. That mission did something no spacecraft had done before it. It used Mercury's own gravity to bend its trajectory back around for a second look, and then a third, squeezing 3 close encounters out of a single launch. Decades before, gravity assist became a routine word in mission planning. Decades later, an orbiter settled into place around Mercury for 4 years of continuous mapping before it was deliberately allowed to fall into the planet's surface, out of fuel, at the end of its mission. A third mission is in transit even now, threading a long sequence of flybys past Earth, Venus, and Mercury itself before it finally has enough energy to slow down and stay in orbit, rather than simply passing through. A reminder that even reaching the closest planet to the Sun still takes years of patient orbital maneuvering rather than a straight line. Venus has seen far more traffic than its reputation as a wasted twin suggests. Dozens of missions, American, Soviet, European, Japanese, have flown past it, orbited it, or dropped straight through its atmosphere since the early 1960s. 10 Soviet landers in particular did something almost no one remembers correctly. They did not just visit Venus. Cameras rolling and instruments recording for as long as their hardware could withstand what waited on the ground, in an era when doing so at all required solving heat and pressure problems no engineering team had previously had reason to study. The first of them to survive landing and transmit did so in 1970. 5 years after that, another lander in the same program returned the first images ever taken from the surface of another planet. Grainy, black and white, showing flat volcanic rock stretching to a horizon under a sky the color of an overcast afternoon. sent back before the extreme heat silenced the transmitter less than an hour later. Through the 1980s and into the early 1990s, an American orbiter used radar rather than ordinary cameras to map the entire planet's surface through its permanent cloud cover, spending years slowly building up a global picture, pass by pass, of volcanoes, highlands, and vast lava plains that no visible light photograph taken from orbit could ever have captured. Japan added its own orbiter in the following decade. This one built specifically to study Venus's atmosphere and its ferociously fast, planet-circling winds rather than the surface underneath them. Mars is the world most people picture when they hear, "We've been there," and for good reason. The first successful flyby returned only a handful of grainy frames in 1965. A later orbiter mapped the whole planet by 1971. And in 1976, two landers touched down within months of each other, the first spacecraft to survive a landing on Mars and operate there for any meaningful length of time. From the late 1990s onward, at least one active orbiter has kept a continuous, uninterrupted presence around Mars, joined over the following decades by a rotating cast of rovers, each one bigger and more capable than the last. A small, wheeled probe barely larger than a microwave oven in 1997, a pair of golf cart-sized twins in 2004, and eventually, car-sized laboratories on wheels in 2012 and 2021 that have driven, drilled, and chemically analyzed rock across dozens of kilometers of terrain. One of those later missions even carried a small helicopter as a hitchhiking experiment. And in 2021, that helicopter lifted a few meters off the Martian surface and flew, the first powered, controlled flight of any kind ever achieved on another planet, using blades spun fast enough to find purchase in an atmosphere barely 1% as thick as Earth's. All of it, together, has become an accomplishment so routine now that a new landing barely makes headlines anymore. That routine took decades and dozens of missions, more than half of which failed outright, to earn. Then, the outer solar system, where visited starts to mean something thinner. Jupiter first felt a spacecraft's presence in December 1973, when the first probe ever to cross the main asteroid belt without being destroyed by a collision arrived for a fast flyby that sent back the first close photographs of a planet larger than every other planet in the solar system, combined. A second, near-identical spacecraft followed roughly a year later, then continued on past Jupiter to become the first of anything built on Earth to reach Saturn as well, proving that a single mission really could be aimed at more than one giant planet in sequence. An orbiter arrived at Jupiter in the mid-1990 seconds and circled the planet for the better part of a decade. At one point, releasing a small probe that fell directly into the atmosphere in December 1995, transmitting data on temperature, wind, and composition for just under an hour before the crushing pressure and heat destroyed it. The closest anything has ever come to landing on Jupiter, and a landing that only a disposable, unmanned probe could have survived attempting at all. A newer orbiter, arriving in 2016, continues studying Jupiter's interior and magnetic field today, and a European mission launched in 2023 is now crossing the long gap toward Jupiter's icy moons, expected to arrive in the early 2030 seconds. Saturn's story adds a genuine wrinkle to the whole idea of landing. Two flybys, a year apart in the late 1970s, were followed by a single orbiter that arrived in 2004 and spent 13 years circling the planet and its rings, returning more data on Saturn than every other mission in history combined, before mission planners deliberately steered it into the atmosphere to burn up in September 2017, ending things on Saturn's own terms, rather than risk it drifting uncontrolled into one of the planet's potentially life-bearing moons. But that orbiter also carried a passenger, a small European-built probe that separated in December 2004, descended by parachute through the thick orange haze of Saturn's largest moon, and actually touch down on a solid, if frigid, surface, transmitting images and data from the ground for well over an hour before its batteries finally failed. It remains, to this day, the only successful landing ever achieved anywhere in the outer solar system. And it happened not on a planet at all, but on a moon, a distinction that turns out to matter more than it sounds like it should. And then there is the edge of what anyone has ever done. Uranus and Neptune have each been visited exactly once, not orbited, visited, in the narrowest possible sense. A single spacecraft passed close enough, once, to take pictures and measurements before continuing on, forever, into darker space. No mission has ever gone back. None is currently funded to. For 2 entire planets, humanity's complete body of close-up knowledge rests on a handful of days of data each, gathered once, decades ago, by a spacecraft that was never designed to return, using cameras and instruments that were cutting edge for their era and have not been improved upon with fresh data since. It is easy to let that single sentence, visited once, decades ago, slide past without registering what it actually means for how little is known. Every other planet in this list has had its early photographs superseded, corrected, and vastly expanded by later missions with sharper instruments and closer approaches. Uranus and Neptune never got that second pass. The best images and measurements available for either world, as this film is being made, are the same ones gathered during those few days in the 1980s, viewed and reviewed by generations of scientists who have had to build entire careers' worth of theory on a dataset that has not grown since. Even the 2 planets with the thinnest record share a small, telling asymmetry with each other. Uranus was reached first, in January 1986. After 9 years of travel, Neptune came 3.5 years later, in August 1989, at the very end of the same spacecraft's mission, on a trajectory calculated years in advance to make use of Uranus's own gravity as a final boost outward. Every image and measurement anyone on Earth has of either planet's clouds, moons, or magnetic field comes from that single, narrow window in each case. A few days of close approach, bracketed by years of empty crews on either side, never repeated since. Say all of that together and it sounds like completion. A checklist with every box filled. But notice what visited was doing across that list. For Mercury, Venus, and Mars, it meant orbiting. For Jupiter and Saturn, it mostly meant circling from a distance, occasionally diving close, once sending something to be destroyed on purpose, just to see what it would find on the way down. And once, remarkably, actually landing, but only on a moon borrowed from the planet's own entourage rather than on the planet itself. For Uranus and Neptune, it meant one brief pass, never repeated, never revisited. The tour is complete only if visit is allowed to mean 5 or 6 different things, depending on which world is being discussed. That flexibility is invisible when the subject is a machine, because a machine never asks which definition it's being held to. It becomes the entire question the moment the subject is a person who has to decide, in advance, which of those definitions they're willing to risk their life on. Because nobody boards a spacecraft on the promise of a visit without first asking, quietly, what that word is actually going to cost them when they arrive. A spacecraft that reaches a planet has satisfied one demand. Arrive, in working order, long enough to do its job. It does not need air. It does not need food, water, or a reason to keep going. It does not need to sleep, does not get bored, does not miss anyone, does not age in any sense that matters to a mission planner watching from a control room on Earth. If a trip takes 12 years, that is a scheduling problem, not a survival problem. The hardware does not experience the 12 years the way a passenger would. It simply exists, mostly dormant, occasionally waking to check its own systems, until the moment it is needed again, indifferent to how much time has passed in the meantime. This was true even before spacecraft ever left Earth's orbit. when the very first attempts at spaceflight already exposed the gap. Long before any human being flew, a handful of the earliest launches carried living passengers instead. Dogs, in the case of the first spacecraft ever to reach orbit, sent up specifically to find out whether a biological body could survive the launch, the weightlessness, and the return at all. The mission answered a question no purely mechanical payload would ever have needed to ask. It also could not answer that question without keeping something alive, feeding it, monitoring its heartbeat, and eventually bringing it home or accepting that it would not come home. A category of problem that a camera or a radio transmitter launched on the very same kind of rocket simply does not have and never will, regardless of how far spaceflight technology eventually advances. If the radiation environment along the way is harsh, engineers shield the specific components that cannot tolerate it and accept gradual degradation in the parts that can fail a little without ending the mission. A processor that slowly accumulates radiation damage over a decade is a known, budgeted risk, planned for with redundant systems, error-correcting memory, and conservative margins built in from the design phase. Engineers can even calculate, in advance, roughly how many stray bit flips a spacecraft's computer will suffer per year from cosmic ray strikes and simply design the software to detect and correct them automatically. Most spacecraft carry entire duplicate copies of their most critical systems for exactly this reason. A second computer, a second radio, a second set of thrusters, wired to switch on automatically the instant the primary fails, so that a single point of damage does not end the mission. There is no equivalent budget for a human cell slowly accumulating the same kind of damage. There is no redundant version of a person's bone marrow waiting in reserve. No backup nervous system that switches on if the first one degrades. No software patch for a mutation that takes root and waits 20 years to become a diagnosis. If the destination has no surface to land on, a flyby or an orbit still counts as complete success. There is no instinctive, embodied need to actually stand on the thing being studied, no sense of a mission left unfinished because no boots ever touched ground. Consider, too, what a machine is permitted to do that a person never could be: fail quietly and stay failed. When a probe's instrument stops responding, mission controllers note it, work around it, and continue the mission with reduced capability until the spacecraft is eventually declared complete or lost. Entire multi-billion-dollar missions have flown for decades on a fraction of their original instrument suite, adapting around dead sensors and stuck mechanisms, rather than treating any single failure as the end of the story. A human body does not get that kind of graceful degradation built into its job description. A single organ failure, a single untreated infection, a single structural injury in an environment with no hospital and no way to evacuate does not become reduced capability. It becomes an emergency with no comparable fallback plan, thousands or millions of kilometers from the nearest doctor, decided in hours by whatever medical training and equipment happened to be packed before launch. None of that is a criticism of the machines. It is the reason they could go everywhere in the first place, decades before anyone seriously discussed sending a person to do the same job with the same technology. A probe's job description is short: survive the transit, execute the sequence, transmit the data, and if possible, keep going afterward in case anyone finds a use for what's left. A human traveler's job description carries all of that, entirely unchanged, and then something else layered on top of it. A body that needs a stable temperature within a narrow band, a breathable mixture of gases at a specific pressure, a radiation dose spread thin enough to still leave a normal life expectancy on the other side, a way to keep muscle and bone from wasting away in the absence of the gravity they evolved under across hundreds of millions of years. And psychologically, some kind of livable relationship with distance and time that simply does not exist for a piece of aluminum, silicon, and solar panels. There is also no equivalent for a human traveler of simply switching a machine off between tasks. A spacecraft cruising towards Saturn for 6 years spends most of that time in a low-power sleep state. Its systems quiet, its instruments off, waking only for scheduled checks and course corrections. A human crew cannot be powered down between checkpoints. Every one of those 6 years has to be filled with something: work, exercise, maintenance, rest, company. Because a mind left with nothing to do for that long does not idle gracefully the way a dormant computer does. It becomes its own operational risk. Notice, too, that this gap does not stay the same size as a mission gets longer. It grows, and it grows in a direction that favors the machine every time. A probe's list of needs is essentially fixed, whether the trip takes 1 year or 12. The same navigation checks, the same data transmission schedule, repeated on the same interval, regardless of distance. A human crew's list of needs compounds, instead of repeating. Every additional year in transit is another year of accumulating radiation dose, another year of bone and muscle quietly thinning, another year of consumables that have to be carried, recycled, or manufactured, another year of the same small group of people needing something to occupy their minds so that boredom and isolation do not become their own kind of failure, and another year in which any one of those slow processes could tip from manageable into dangerous without much warning. A probe on a 12-year cruise and a probe on a 2-year cruise are, from an engineering standpoint, doing almost the same job for different lengths of time. A crew on a 12-year cruise is not doing the same job as a crew on a 2-year cruise at a larger scale. They are doing a categorically harder one, because nearly every one of their requirements gets worse with time in a way that a machine simply does not. This is the fork the rest of the story runs on, every constraint that follows. Propulsion, radiation limits, hibernation research, the search for artificial gravity exists because engineers are trying to close the gap between what a machine already tolerates by default and what a body has never once been asked to tolerate, anywhere in the entire history of the species. Even the most demanding spaceflight endured so far, months at a time aboard a station orbiting a few hundred kilometers above Earth's surface, still sits well inside the planet's protective magnetic field, with a rescue vehicle always docked and ready, and a return to Earth always less than a day away in an emergency. Nothing about that experience, however uncomfortable, resembles being a decade into a one-way transit with no possibility of turning back, no resupply ship on standby, and no atmosphere or magnetic field standing between the crew and deep space at all. Reaching a planet turned out to be the easy part, historically speaking. Machines proved that repeatedly, at every distance the solar system offers, using technology that in some cases predates the personal computer by years. The hard part, the part still unsolved for most of these worlds, is keeping a person alive long enough, coherent enough, and intact enough to be the one who actually arrives, and then keeping them that way for however long it takes to come back, if coming back was ever part of the plan at all. There is a quieter version of this same gap worth naming before moving on, because it will resurface in almost every chapter that follows. A machine never has to be convinced that a mission is worth what it costs. It has no stake in the outcome beyond whatever its instructions specify. A human crew does. And that stake is not a soft, sentimental detail. It is a design requirement in its own right. Every fix this story is about to examine, from better rockets to shielding to engineered sleep, is ultimately an attempt to make a specific kind of promise credible to the people who would have to live inside it, that the years asked of them will end in something recognizable as a life afterward, not just a successful transmission back to Earth. None of the 5 items on that list can be satisfied once and then forgotten either. A probe's requirements are front-loaded: survive launch, survive cruise, execute the sequence, and once satisfied, the mission is essentially in the clear, regardless of how long it continues afterward. A person's 5 requirements have to be met continuously, every hour, for the entire length of the mission, with no moment at which the body is finished needing them. Keep that list in mind, because it is short enough to hold on to for the rest of this story. Temperature, air, radiation, gravity, and time experienced as a person rather than logged as a timestamp. Every planet examined from here forward will be measured against exactly those 5 requirements, one at a time, in addition to the distance and cost already on the table. A probe never had to clear that bar. A human traveler has to clear all 5 simultaneously for as long as the mission lasts. And the rest of this film is, in a very real sense, an audit of how many planets can actually clear it. Distance in space is not measured only in kilometers. It is measured in the energy required to change velocity. Engineers call it delta V, and it behaves less like a straight-line road trip and more like a series of toll booths stacked one after another, each charged in the currency of propellant a rocket has to carry with it from the very moment it leaves the ground. Leaving Earth's gravity well costs a fixed, brutal amount no matter where the destination is. A spacecraft has to accelerate to over 11 kilometers per second just to stop falling back down, before a single unit of energy has been spent actually going anywhere. The cheapest, most fuel-efficient way to reach another planet is a long, looping elliptical path that touches the departure orbit at one end and the destination orbit at the other. A minimum energy route named after the German engineer who worked out its mathematics in the early 20th century. It is efficient precisely because it is slow. Rather than fighting the sun's gravity head-on, a spacecraft on this kind of trajectory essentially coasts, letting orbital mechanics do almost all of the work over months or years, spending fuel only at the beginning and, if needed, at the end. Faster routes exist, but they cost disproportionately more propellant for every extra kilometer per second of speed because of a stubborn mathematical relationship between velocity and fuel mass that rocket engineers have wrestled with since the earliest days of the field. Pushing for meaningfully more speed does not add fuel in a straight line. It multiplies it, which is part of why so many missions accept the slower, cheaper route rather than the fast, uneconomical one. A full delta V budget for any real mission is not one number, but a sum of several smaller ones, each corresponding to a specific maneuver. Escaping Earth's gravity, coasting through the transfer orbit, correcting course along the way, as tracking data refines the spacecraft's actual position against its planned one, slowing down to be captured by the destination's gravity rather than flying past it, and, if a landing is planned, slowing down again all the way to a stop on the surface. Skimp on any one of those line items and the mission does not partially succeed. It misses the planet entirely, or arrives too fast to be caught by its gravity, or arrives safely in orbit with no way left to actually descend. Reaching Mars costs a delta V budget in the neighborhood of 5.5 to 6 kilometers per second, once departure and orbit insertion are both counted. Demanding, but a number decades of missions have already met, repeatedly, using nothing more exotic than chemical rockets and a patiently chosen transfer window that only opens roughly once every 2 years when Earth and Mars happen to align correctly. Reaching Jupiter roughly doubles that figure, largely because a spacecraft first has to escape not just Earth's gravity, but a much deeper stretch of the Sun's own gravity well before Jupiter's pull can meaningfully take over. Reaching Saturn requires something on the order of double Jupiter's number again. By the time the destination is Uranus or Neptune, the raw delta V for a direct trajectory climbs into a range so punishing that no mission has ever attempted it without borrowing energy from the planets along the way. Swinging past Jupiter or Saturn to steal a fraction of their own orbital momentum, a technique called a gravity assist, the same trick that let one spacecraft complete its full grand tour of all 4 giants, using an alignment that will not repeat again for well over a century. Translate that energy cost into something more human: time. With today's chemical propulsion, a one-way trip to Uranus takes roughly a decade. A direct trip to Neptune, without help from other planets along the way, does not comfortably finish in less than 15 years. And no chemical trajectory on record beats that number by any meaningful margin. The spacecraft that did reach Neptune only managed a 12-year transit because it borrowed velocity from Jupiter, Saturn, and Uranus in sequence, threading a chain of gravitational favors that will not be geometrically available again in most living people's lifetimes. For comparison, the fastest spacecraft ever launched from Earth, built specifically to reach the outer solar system as quickly as physically possible, with almost no other mission objective competing for its fuel budget, launched directly on a trajectory requiring no early course correction detours. Still needed roughly 9.5 years just to reach Pluto, which sits closer to the Sun than Neptune does for most of its orbit. Electric propulsion, a slower, steadier kind of thrust than a chemical rocket's brief violent burn, works by accelerating a small amount of propellant to very high speed using electricity rather than combustion, trading raw power for extraordinary efficiency over long stretches of time. It can shave meaningful time off an outer planet transit, potentially cutting a Neptune trip closer to a decade instead of 15 years. But meaningful here still means years shaved off years, not months shaved off years. Compare that decade plus of one-way travel against the mission humanity already treats as its most ambitious, realistic goal. A Mars round trip, at 2 to 3 years, already sits at the outer edge of what current mission planning considers an acceptable stretch of time to keep a small crew healthy, supplied, and psychologically stable, and it has never actually been attempted with people aboard. Every serious Mars mission architecture published so far treats that duration as a genuine engineering and human challenge in its own right, requiring redundant life support, a large enough crew to share the workload and the social burden, and enough consumables or in-situ production to survive months on the surface, waiting for the next return window to open. And even these carefully engineered proposals still describe the mission as pushing against the outer edge of what current systems and current medical knowledge can confidently support. A trip to Uranus or Neptune does not stretch that same challenge. It replaces it with one 4 to 6 times longer, one way, before any of the same open questions about crew health and supply have even been resolved at the shorter distance. Hold those numbers next to a human lifetime, and the arithmetic changes character entirely. A round trip to Mars, using propulsion available today, already asks for roughly 2 to 3 years of a person's life. Most of it spent either accelerating away from everything familiar or waiting, in orbit, for the next transfer window home to actually open. Since departure windows are dictated by planetary alignment rather than personal readiness. A one-way trip to Neptune, even in the optimistic case, asks for more than a decade before the person has done anything except arrive. Add a return leg, which no current mission design for this class of destination even assumes, because no one has yet designed a full round-trip mission architecture for it. And the number stretches well past what most people would call a normal career, let alone a single expedition. A person who left for Neptune in their early 30s, on the most optimistic transit numbers available, would not complete a round trip before their own health, independent of any mission risk at all, had already changed the terms of the question entirely. Picture what that decade actually contains for the traveller rather than the mission planner. It is not one long dramatic journey. It is thousands of identical quiet days inside a small pressurized volume, watching the same handful of faces, performing the same maintenance checks, waiting for messages from Earth that arrive hours late one way, hours later still coming back, so that even a simple conversation stretches into something closer to an exchange of letters than a phone call. Birthdays pass without anyone new to celebrate them. News from home arrives as history rather than updates. This is the reversal buried inside the achievement from Chapter 1. The fact that a probe visited Neptune in 12 years does not mean a human mission could match that pace on equal terms. A probe's 12 years cost nothing but patience from a control room on Earth, staffed by people who go home every evening to their own lives, their own beds, their own families, while the mission quietly continues without them in the background. A human crew's 12 years cost a decade of each traveler's one life spent in transit before the mission has even started asking anything of them. A decade during which everyone they left behind keeps aging, keeps changing, keeps living an entire chapter of a story the traveler will only hear about, in fragments, delayed by hours of radio lag, whenever there is anything left worth saying, and keeps doing so whether or not the traveler is there to witness any of it firsthand. Distance by itself was the smaller half of the obstacle. The larger half is what distance costs a body that has to be kept alive, coherent, and, in most versions of this story, anyone would consider worth living, eventually brought home for every single one of those years. It is worth being precise about what closer to a decade actually buys. In exchange for what it costs, electric propulsion systems generally produce far less raw thrust than a chemical engine, which means a spacecraft using them accelerates gradually rather than all at once, often spending months just building up to a meaningful fraction of its final speed before it can even begin coasting toward its destination. Shaving years off a Neptune transit this way does not mean a faster departure or a more dramatic launch. It means trading a short, violent chemical burn for a long, patient electrical push, sustained by a power source that itself has to survive the entire journey without failing. None of that arithmetic is likely to improve quickly either. The delta V figures and transit times used throughout this chapter come from trajectories and propulsion systems already flown or already engineered and tested on the ground, not from a hoped-for future breakthrough. Any real reduction in the human cost of distance has to come from somewhere specific. A genuinely more efficient way to convert stored energy into thrust, sustained over the whole length of a transit rather than in the initial burn alone. And precisely the kind of fix that, examined closely, turns out to buy back time only by creating new problems of its own. There is a second cost layered on top of distance, and it is harder to picture than a delta V number or a transit time calendar, because it leaves no mark until much later: radiation. A rocket either has enough propellant or it does not, and the answer is known before launch. A dose of radiation does not announce its consequences on a schedule anyone can predict. It accumulates silently, in tissue, over years, and the bill can arrive decades after the mission that generated it has already been called a complete success. Beyond the protection of Earth's magnetic field and thick atmosphere, space is soaked in two kinds of ionizing radiation that almost never reach the ground in dangerous amounts back home. The first is a steady, unavoidable background of galactic cosmic rays, arriving from outside the solar system entirely, moving fast enough and carrying enough raw energy that even fairly thick shielding barely slows the most energetic examples down. The second is far more sudden and unpredictable. Bursts of charged particles thrown out by the sun itself during flares and coronal mass ejections, capable of raising the ambient radiation level in a spacecraft dramatically within a matter of hours, with only whatever advance warning current solar monitoring satellites can provide. Earth's own magnetic field does not distribute its protection evenly, which is itself a clue to how uneven this problem becomes once a spacecraft leaves it behind. Close to the planet, that field traps charged particles in two donut-shaped bands circling the equator, regions dense enough with radiation that satellites are deliberately routed around the thickest parts of them rather than through. A spacecraft heading to Mars, Jupiter, or beyond has to climb out through the outer edge of that trapped radiation and then keep going. No belts, but also no shelter. Just a steady, unfiltered exposure for as long as the transit lasts. A spacecraft's electronics can be hardened against both, or simply allowed to accept a shortened working life as an acceptable trade-off written into the mission plan from day one the same way engineers accept that a probe's cameras or sensors might slowly degrade over a decade-long mission. Beyond shielding, researchers on the ground have also spent years investigating whether certain compounds, taken before or during exposure, might help cells resist or repair some of the damage radiation causes, a pharmacological countermeasure rather than a purely physical one. That research remains early, tested mostly in cell cultures and animals rather than in astronauts, and no such countermeasure is currently approved or relied upon as part of any actual mission's radiation protection plan. Which means every real mission flown to date has depended on shielding and dose limits alone, with no pharmacological backup to fall back on. A human body cannot be hardened in any comparable sense to a circuit board. It can only be shielded, and shielding has its own brutal arithmetic. Mass. More protection means more mass, and more mass means more propellant, which loops directly back into the same delta V problem distance already created in the previous chapter. Worse, some of the densest, most obvious shielding materials like aluminum can actually make the problem slightly worse for the fastest, most energetic cosmic rays. The collision itself shatters the incoming particle into a spray of secondary radiation that can do comparable, sometimes worse, damage to the tissue sitting behind it. A counterintuitive result that took real testing, not intuition, to uncover. Since more shielding mass is not automatically better shielding. The materials that work best tend to be lighter. Hydrogen-rich substances like water, liquid hydrogen, or certain dense plastics, which is part of why some mission concepts propose lining crew quarters with the spacecraft's own drinking water supply or food stores, turning cargo the mission already has to carry anyway into a radiation shield at effectively no extra mass cost. This is also why radiation risk resists the kind of clean, universal number that a delta V budget offers. Cancer risk from a given dose depends on age at exposure, on which organs absorb the most energy, on genetic factors no pre-flight screening can fully account for, and on decades of subsequent life, during which the damage either does or does not express itself as disease. Two astronauts who receive an identical physical dose on the same mission can walk away with meaningfully different real-world risk. For reasons medicine can describe only in probabilities, not certainties, which is part of why setting a single career limit for an entire astronaut corps, as opposed to a personalized one, has always been as much a policy judgment as a purely scientific one. In 2022, the agency that runs the most human spaceflight missions in history revised its official safety threshold, a career limit, for any astronaut, regardless of age or sex, of under 600 millisieverts of accumulated effective dose. A single, uniform ceiling replacing an older, more permissive standard that had varied by age and by sex for decades, on the reasoning that younger astronauts and women had more remaining lifetime in which a radiation-induced cancer could develop. That number was not chosen as a nice round figure. It is calibrated to keep a person's added lifetime cancer risk from spaceflight radiation below a specific, small threshold above their ordinary baseline risk of developing cancer over a full life. Now place a realistic Mars mission against that ceiling. Astronauts aboard a space station in low Earth orbit, still comfortably inside the partial protection of the planet's magnetic field, already absorb far more radiation per day than anyone standing on the ground, but nowhere near the levels waiting in true deep space. Current estimates for a long-duration round trip to Mars, accounting for the transit both ways and time spent on the surface, put the accumulated dose at roughly 1 sievert or more, depending heavily on how much shielding the spacecraft carries, and where the mission happens to fall in the Sun's roughly 11-year activity cycle, since a more active Sun paradoxically pushes away some of the most energetic galactic cosmic rays even as it raises the risk of a dangerous flare. 1 sievert is 1,000 millisieverts. The career limit is under 600. A single mission to the nearest planet with any plausible human itinerary can, by itself, exceed the lifetime safety ceiling. An astronaut is supposed to stay under for their entire career, and that estimate does not even fully account for an unshielded solar particle event, which could deliver a dose in a matter of hours far beyond anything a radiation worker on Earth would ever legally be allowed to absorb in a lifetime. The two kinds of radiation also do not respond to the same countermeasures, which complicates any single fix even further. A solar particle event, however dangerous in the moment, arrives from a roughly known direction and tends to be preceded by at least some warning from solar observatories, which means a mission can plan a small, heavily shielded storm shelter compartment, built from the densest available materials, even if too heavy to use for the whole crew habitat, where the crew retreats for the hours or days a flare event lasts. Galactic cosmic rays offer no such escape. They arrive from every direction, continuously, at energies high enough that no shelter compact enough to build into a real spacecraft blocks more than a fraction of them. A storm shelter solves the emergency. It does nothing for the steady, unglamorous background dose that keeps accumulating every single day of the transit. Flare or no flare, the part of the radiation problem this chapter's numbers are ultimately about, and the part no single engineered room can simply wait out. This is not a problem that disappears the way a delta V problem can, by throwing more propellant at it. Shielding scales with mass. Mass scales the cost of getting there, and the destinations only get harder from Mars outward. Longer transit times mean longer cumulative exposure, and outer solar system missions offer none of the modest partial shelter that a thin Martian atmosphere at least provides during descent and short-duration surface operations. A probe simply tolerates its dose, or fails a few years earlier than planned, and either outcome is an acceptable line item in a mission budget written years in advance. For a person, the dose does not show up as a mission failure at all. It shows up decades later, quietly, in a body that came home successfully and kept living with whatever the exposure had already set in motion, long before anyone could measure it or tell. Picture the actual shape of that risk, rather than just its number. A returning Mars astronaut, on the current best estimates, does not come home with a diagnosis. They come home cleared for duty, celebrated, physically intact by every test available at the time. What they carry instead is a shifted probability, a small but real increase in the chance that 10 or 20 or 30 years later, in an otherwise ordinary decade of their life, a cell that absorbed a stray particle over the Martian transit finally becomes the origin of a disease no one can trace back to a single moment. That is a strange kind of cost to ask someone to accept in advance. Not a guaranteed price, but a raised likelihood, payable on a schedule nobody controls. For a homecoming that will look, on the day it happens, like nothing went wrong at all. It is worth noting, too, what this dose bill does not include: the additional exposure from time actually spent on a planet's surface, walking, working, and sleeping outside the thickest parts of a spacecraft's shielding in a habitat that itself has to be light enough to have been landed there in the first place. Surface operations typically add to the transit dose rather than pausing it, particularly on a world like Mars with only a thin atmosphere and no global magnetic field of its own to provide any additional shelter. Every chapter that follows this one has to be read against that same quiet backdrop. Radiation does not disqualify Mars or any other destination outright. It raises the price of admission in a currency that does not show up on a mission patch or a budget spreadsheet, and it raises that price fastest for exactly the destinations that already demanded the most time in transit to begin with. None of this has stopped people from trying to design around it, and for a while, several of those designs look genuinely promising enough that, examined one at a time, each seems capable of closing the exact gap the previous chapters just opened. Start with propulsion, because it answers the distance problem in Chapter 3 most directly. Instead of a brief, violent chemical burn that expends almost all its propellant in minutes, A nuclear-powered engine can sustain much higher performance over the course of an entire mission. One version, nuclear thermal propulsion, uses a reactor to heat a propellant like liquid hydrogen to extreme temperatures and expel it through a nozzle, extracting roughly double the efficiency of a comparable chemical engine for the same mass of propellant carried, meaning a spacecraft could reach the same speed with far less fuel, or a higher speed with the same fuel, cutting transit time directly. A related approach, nuclear electric propulsion, instead uses reactor power to run electric or plasma thrusters that produce a much gentler but far more sustained push, building velocity slowly and steadily over months rather than minutes, trading immediate thrust for years of patient, continuous acceleration, closer to a slow, relentless press than a shove. In principle, either approach could meaningfully cut transit times and ease the delta-V burden that makes Jupiter, Saturn, and everything beyond them so punishing. Engineers measure an engine's efficiency with a single figure called specific impulse. Essentially, how much thrust a given engine squeezes out of a given mass of propellant, the rocket equivalent of fuel economy. A typical chemical rocket engine tops out at a specific impulse in the low hundreds of seconds. A nuclear thermal engine can roughly double that, and an electric thruster can reach figures several times higher still, though at far lower absolute thrust. Which is exactly why electric propulsion trades a strong push for a long, patient one rather than a short, violent one. That single number, how much velocity a mission gets per kilogram of propellant carried, is the thread running underneath every transit time figure in the previous chapter, and improving it is the most direct lever available for cutting years off a trip. This is not a hypothetical idea confined to whiteboards and conference papers. As recently as 2023, a joint program between a US Defense Research Agency and the National Space Agency was actively developing a nuclear thermal propulsion demonstrator with an in-space test once targeted for the mid-2022s. A serious, funded, hardware-building effort, not a thought experiment. None of these ideas exist in isolation from each other, either. Part of what makes this moment in the story so persuasive is how naturally they seem to stack. A crew traveling in torpor needs less shielded volume to protect, because a smaller, more tightly packed sleeping compartment is easier to armor heavily than an entire crew habitat built for people who need to move around and work every day. In the same way, a single well-insulated room is cheaper to heat than an entire house. A mission relying on in-situ resources needs less mass launched from Earth in the first place, which frees up mass budget that could go toward a more capable propulsion system or thicker shielding elsewhere. On paper, every fix seems to make at least one other fix a little easier to afford. A better propulsion system that cuts years off a transit also cuts years off cumulative radiation exposure, easing the shielding requirement in turn, which in turn frees up mass that could go toward a larger crew or more redundant life support. A rotating habitat that keeps a crew stronger and healthier reduces the medical margin a mission has to plan around, which loosens the pressure on every other safety system, and a crew that arrives in better physical condition needs less recovery time before they can begin useful surface work at all, which shortens the total mission timeline in a way that compounds with every other saving on this list. It is precisely this kind of mutual reinforcement that makes ambitious engineering programs feel achievable in their early planning stages, years before any hardware exists to test whether the reinforcement holds up under real budgets and real schedules. Radiation shielding, meanwhile, is not a mystery to design in the way propulsion breakthroughs sometimes require genuinely new physics. It is a known set of materials and geometries, refined over decades of studying exactly how different substances absorb or deflect charged particles, and refined further by every human mission that has ever flown in low Earth orbit. Given enough mass arranged in the right configuration, a spacecraft can meaningfully cut the dose its crew receives. layering water tanks, food stores, and dense polymers around the sections of the ship where the crew actually sleeps and works, concentrating the heaviest protection where the body spends the most time and accepting lighter protection in areas used only briefly. In situ resource use offers a different kind of relief entirely, one aimed not at the journey but at what has to be carried along for it. Rather than launching every gram of fuel, oxygen, and water a mission will ever need, this approach proposes manufacturing at least some of those supplies from local materials once a spacecraft arrives. It is not purely theoretical. In 2021, an experiment riding on a Mars rover successfully demonstrated the conversion of Mars's thin, carbon dioxide-rich atmosphere into breathable oxygen, running repeatedly over the following months as a proof of concept for technology that could, at a larger scale, one day produce both breathing air and rocket propellant on the Martian surface itself, dramatically cutting the mass that has to be launched from Earth for a return trip. Water ice detected beneath and even at Mars's surface in several regions adds a second local resource to the same idea, one that could in principle be split into breathable oxygen and usable hydrogen fuel using nothing more exotic than electricity, if a mission ever lands close enough to a large enough deposit to make the extraction worthwhile. Human hibernation research offers a different kind of fix again, aimed less at the ship and more at the traveller. European researchers have spent years studying torpor, a controlled, dramatically reduced metabolic state inspired directly by mammals like ground squirrels and black bears that survive months of winter by lowering their own body temperature and metabolic rate to a fraction of normal, as a way to let a crew essentially sleep through the most dangerous, most tedious stretch of a long transit. If it worked as intended, the approach would not shrink the distance at all. It would shrink the traveler's exposure to the psychological and physiological cost of experiencing that distance minute by minute, day after day, for years at a stretch, while potentially lowering metabolic demand for food, water, and oxygen along the way as well. The European Space Agency has funded studies on exactly this question for over a decade, framing it explicitly as infrastructure for future missions rather than a medical treatment in its own right, and researchers working on it have proposed it could shrink not just consumables but even spacecraft habitat size itself, since a torpid crew needs far less living space, movement, and entertainment than an awake one. And for the persistent problem of weightlessness, wasting away bone and muscle over months or years, engineers have long sketched rotating habitats, spinning structures that use centrifugal force to fake the pull of gravity, letting a crew's body experience something closer to the mechanical loads it evolved under. The physics is simple enough to teach in an introductory course. Spin a structure fast enough, at a large enough radius, and anything standing inside it is pressed outward against the hull exactly the way gravity presses a person down onto a floor. Engineers have studied variations on this idea since at least the 1950s, when an influential rocket engineer first sketched a wheel-shaped station, roughly the width of a city block, rotating slowly enough in orbit that its rim would feel like a gentle version of Earth gravity to anyone standing on it. The idea resurfaced with far more mathematical rigor in the 1970s, when a physicist leading a series of university-affiliated design studies proposed entire cylindrical colonies, some large enough to hold a small town's worth of residents, complete with strips of simulated landscape, weather, and a day-night cycle produced by mirrors reflecting sunlight down the length of the cylinder. Every one of those designs, however different in scale, still runs into the same wall discussed a chapter ahead. The difference between a compelling drawing and a structure that can actually be launched and assembled. Laid out together, these 5 ideas: better propulsion, better shielding, local resource production, engineered dormancy, spin-generated gravity, sound like exactly the kind of layered solution a hard problem eventually gets, each one chipping away at a different chapter's obstacle until nothing structural is left standing in the way. Better propulsion answers the distance problem from Chapter 3. Better shielding and in situ resources answer the radiation and supply problem from Chapter 4. Engineered dormancy and rotating gravity answer the physiological and psychological toll this story has only hinted at so far. Stack them up and Mars stops looking like the edge of what is possible. The distance problem shrinks, the radiation bill shrinks, the supply chain shrinks, and the body itself gets a fighting chance against months of weightlessness. It starts looking like a solved problem waiting only for enough political will and enough funding to become routine. The way orbiting the Earth once looked impossible, and then, within a single working lifetime, became almost mundane. Or the way crossing an ocean by air went from a life-risking novelty to a boarding gate within the span of a few decades. Precedents this story does not dismiss, only asks to be applied to the right destination. For a moment, in the middle of this story, that is a completely fair thing to believe. Every piece of it is real, funded, or at least seriously studied by credible institutions at the time this film was made. None of it is science fiction, and if all 5 of these fixes matured on the timelines their advocates hope for, the case for eventually sending people to Mars, and perhaps much further down the road, even further out, would look considerably stronger than the raw distance and radiation numbers from the previous 2 chapters suggested on their own. Believe it for as long as the moment lasts, because it does not last long. The stacking logic from the end of the last chapter, that each fix makes the others a little easier to afford, is real, but it runs in both directions. Just as surely as one fix maturing makes its neighbors cheaper, one fix collapsing removes the savings every other fix was quietly counting on. Pull one card from that stack, and the whole arrangement has to be recosted from scratch. Take the nuclear propulsion program from Chapter 5, the one with an in-space demonstration once scheduled for the mid-2020 seconds. Announced as a partnership in early 2023, with hardware development proceeding through 2024 and into 2025, the plan called for an actual orbital test of the engine within a couple of years. Then, in 2025, the program was cancelled outright, not because the physics failed, and not because a test article ever malfunctioned. The reasoning given was economic. The cost of reaching orbit had fallen so dramatically over the preceding years, driven largely by commercial launch competition undercutting older cost assumptions, that the agencies involved judged the enormous, multi-year investment required to fully mature nuclear propulsion no longer justified against nearer-term chemical alternatives for a Mars-class mission. A technology capable of reshaping the Delta-V problem for every outer-planet mission described so far in this story was not defeated by engineering. It was defeated by a single line item zeroed out in a single fiscal year's budget proposal, roughly 2 years after active hardware development had begun. A reversal fast enough to make the point on its own. Nothing about the underlying physics changed between the announcement and the cancellation. Only the institutional appetite to keep paying for it over a period shorter than many university degrees. That distinction matters more than it might seem, because it means the setback is reversible in a way a genuine technical failure would not be. A future administration, a future budget cycle, or a future launch cost shift in the other direction could revive the same program on the same physics. It also means no one should treat its cancellation as proof the idea was flawed, any more than its earlier funding should have been treated as proof it was inevitable. That is the pattern worth sitting with. More than the specific program that got cut, these fixes are not stable infrastructure. They exist in a state closer to promising research than working hardware. And promising research is exactly the category of thing that gets cancelled, delayed, or quietly narrowed in scope the moment institutional priorities shift, regardless of how sound the underlying science remains. Human torpor research tells a similar story from a different angle. Not cancellation, but immaturity. The infrastructure needed to properly study hibernation, even in laboratory animals, in microgravity, does not yet exist anywhere in orbit. Torpor has never been induced or studied in space at all, in any organism, mammal or otherwise, which means every promising result so far comes from ground-based labs where gravity, radiation, and isolation are simply absent from the experiment. Researchers involved in the work themselves put the earliest realistic human trials roughly a decade out, contingent on funding that has not yet been secured. And the space agency most publicly associated with crewed Mars planning has explicitly and publicly stated it is not currently preparing to place any astronaut into hibernation, specifically to counter viral claims suggesting otherwise. The idea is real, and the underlying biology is well studied in animals. The runway to make it usable for a human crew simply is not there yet, and no one currently funding it claims otherwise. And even once the biology is better understood, human torpor would still need to solve problems the animal research barely touches. How to safely lower and then raise a person's body temperature and metabolism without a caregiver monitoring them the entire time. How to prevent the same bone and muscle loss a torpid, motionless body would suffer even faster than an awake one exercising daily. And how to wake a crew reliably, on schedule, in an emergency, rather than leaving them unresponsive at exactly the moment a mission might need them most alert. Compounding all of this, the timeline researchers themselves describe earliest human trials roughly a decade out, contingent on funding not yet secured, was published as an optimistic estimate made by scientists advocating for their own field's continued support in exactly the same funding environment that just cancelled a fully built nuclear propulsion demonstrator over cost rather than performance. There is no particular reason to expect torpor research to be shielded from the same budgetary pressure that ended Draco. And every reason, based on the pattern already established in this chapter, to expect it will face the same test eventually, on a timeline set by budget committees rather than by the biology itself. The same kind of committee that just decided, over the course of this very chapter, that a fully built rocket engine was not worth finishing. It is worth being fair to the program while noting what its cancellation actually proves. Nuclear thermal propulsion is not a fringe idea rejected by expert consensus. It had cleared enough technical review to reach active hardware development inside two of the most scrutinized engineering bureaucracies in the world. Its cancellation says nothing at all about whether the reactor would have fired correctly, whether the thrust figures would have matched the models, or whether the demonstrator would have survived its planned orbital test. Its cancellation was not a verdict on whether it would have worked. It was a verdict on whether it was worth continuing to pay for, made by people comparing it against alternatives that did not exist, in those terms, a decade earlier. That is precisely the kind of judgment that can reverse again just as quickly, in either direction, which is exactly why no chapter in this story treats any funding decision as permanent, only as the honest state of things at the moment this film was made. The in situ resource idea from Chapter 5 fares better, but only within strict limits. The oxygen generation experiment that succeeded on Mars worked specifically because Mars has a thin but genuinely present atmosphere rich in carbon dioxide, a raw material the technology was built to consume. That same chemistry simply does not exist at Venus's surface in any usable form, nor on any of the gas or ice giants, where there is no comparable local atmosphere composition to exploit in the same way, and no surface at all to build a production facility on in the first place. A fix proven at one planet does not automatically transfer to the next one. Rotating habitats face a quieter but equally stubborn obstacle: mass, combined with an uncomfortable side effect. Spin a structure too small, too fast to generate enough force, and the difference in apparent gravity between a person's head and their feet becomes strong enough to cause dizziness and nausea. The same effect that makes a fast merry-go-round unpleasant, just scaled up to something a crew would have to tolerate for years rather than minutes. Avoiding that discomfort means building the rotating section large, on the order of 100 meters or more in radius, spinning slowly rather than quickly. A structure large enough to spin comfortably strong enough to hold together under that spin, and light enough to actually launch from Earth in pieces and assemble in orbit has never been built because large enough and light enough pull in opposite directions at exactly the scale a real interplanetary habitat would require, and no rocket in existence today can lift a finished structure of that size in a single piece. Building it in pieces instead only trades one unsolved problem for another. It means dozens of separate launches, each one adding cost and risk, followed by an orbital assembly campaign. Welding, docking, and pressure testing a structure larger than anything ever assembled in space before, using construction techniques that, at this scale, exist only as engineering studies rather than flight-proven procedure, tested in practice on nothing larger than the far smaller stations humanity has assembled in orbit so far. And shielding remains bound by the same law it always was. Protection scales with mass scales with cost, and the destinations that would benefit most from heavier shielding, the ones with the longest transit times, are, by the arithmetic already laid out in Chapter 3, also the destinations that already cost the most just to reach in the first place, before a single extra kilogram of protection is added to the design. Doubling a spacecraft's shielding does not simply double the mission's cost. It also means more propellant to accelerate that extra mass, which means a larger propulsion system, which itself needs more structural support and, in turn, more shielding of its own to keep the crew safe from its own reactor or engine components. A compounding tax that makes just add more shielding a far less simple answer than it sounds the first time it is proposed, and one that gets worse, not better, the farther the destination sits from Earth. Even that everything stacks nicely together, optimism from the end of the last chapter deserves a second look under this same pressure. It is true that a torpid crew needs less shielded volume, and that in situ resources reduce launch mass. It is equally true that none of those savings exist yet in any flight-proven form, which means a real mission planner cannot bank them the way a hopeful sketch can. Every one of the interlocking savings from Chapter 5 is itself a bet on a technology from this same list maturing on schedule, which means the whole stack is only as reliable as its shakiest single piece. And this chapter has just shown that the nuclear propulsion piece, at least, is currently not a piece at all. Cancelled, not merely delayed, with no funded successor yet announced to take its place. None of these 5 solutions failed because they were bad ideas. Each one failed to become working infrastructure or remains limited to a single narrow application. Because, examined closely, it turns out to be a second engineering problem roughly as hard as the first one it was meant to solve. And every one of them remains exposed to something no rocket equation accounts for anywhere in its math. Political and budgetary priorities that can zero out a decade of progress in a single fiscal year for reasons that have nothing whatsoever to do with whether the underlying technology actually works. Set the funding politics aside for a moment and look only at what current medicine and physiology actually know, because even a fully funded version of every fix from Chapter 5 runs into a wall that money alone does not move. The human body was never designed for any of this, and long-duration spaceflight keeps returning the same warnings every time it is studied closely. On missions vastly shorter than anything this story has been describing, everything known about how a person's body responds to months in space comes from missions lasting, at most, a year or so, aboard stations that remain inside Earth's protective magnetic field the entire time. An outer planet transit would not extend that experience modestly. It would multiply it by a factor of 10 or more, into a regime where nobody has ever actually measured what happens to a human body, only extrapolated from what happens over a much shorter stretch. Extended weightlessness reliably degrades bone density and muscle mass in astronauts, even aboard a space station with rigorous daily exercise regimens built specifically to fight it. The best countermeasures available today slow the damage. They do not stop it. and weight-bearing bones in particular can lose a meaningful percentage of their density for every month spent without gravity's mechanical load, a rate that would compound seriously across a multi-year outer planet transit, long after any short mission exercise protocol was designed to handle. Cardiovascular systems, no longer required to pump blood upward against gravity, begin to deteriorate in ways that complicate a safe return to any planet's surface, including Earth's. After long enough in orbit, some returning astronauts struggle to stand upright for their first minutes back under gravity. Their circulatory systems, having quietly adapted to an environment where blood no longer needs to be pushed uphill, a condition doctors call orthostatic intolerance, generally temporary on Earth after a short mission, but untested at the scale a decade in transit would demand, and considerably more dangerous for a crew that would need to walk off a lander onto an unfamiliar surface, rather than being carried out on a stretcher by a waiting recovery team, as returning astronauts on Earth often are. A significant fraction of astronauts on long-duration missions also develop measurable changes to their vision, caused by fluid shifting toward the head in the absence of gravity and putting sustained pressure on the eyes and optic nerve, a condition well documented enough now to have its own name in the medical literature, spaceflight-associated neuroocular syndrome, and one with no fully reliable countermeasure yet identified. Researchers studying astronauts returning from long-duration missions have also documented measurable changes in immune system function during spaceflight, including the reactivation of otherwise dormant viruses that a healthy immune system on Earth normally suppresses without any symptoms at all, a sign that whatever is happening to the body in microgravity reaches well beyond bones and muscles into systems no exercise regimen is designed to protect. None of these findings are exotic or disputed among researchers who study them. They are the routine, repeated output of the closest thing spaceflight medicine has to a long-running clinical trial drawn from decades of missions and hundreds of astronauts. That is precisely what makes them so hard to argue past. This is not a single alarming study awaiting replication. It is the consistent baseline every mission adds another data point to. And the sample size, while still small, by the standards of ordinary medical research, has been accumulating for well over half a century of continuous human spaceflight, without ever once producing a mission-length data point that contradicts the basic pattern. A longer time away from Earth's gravity and magnetic field means more of every effect described in this chapter, not less, and not a plateau. If anything, longer missions have consistently uncovered new effects that shorter ones were not long enough to reveal at all, which is precisely the wrong direction for anyone hoping the body eventually adapts and stabilizes given enough time. Radiation exposure at the levels discussed in Chapter 4 carries elevated cancer risk that current research still cannot fully quantify for a mission length beyond anything yet flown by a human being. Every existing dose model is, to some degree, an extrapolation past the actual lived experience of any astronaut in history, built from shorter missions and animal studies, rather than direct human data at the doses an outer planet mission would involve, which means the actual risk could turn out better or worse than current models predict, and no crew would know which until it was far too late to change course. A level of open uncertainty no mission has ever had to accept on top of everything else already asked of it. And isolation itself, months or years spent with the same small crew, growing more physically distant from Earth with every passing week, unable to leave, unable to call for help that could arrive in anything less than months, is its own unresolved variable. A widely cited 520-day isolation experiment, completed in 2011, in which a small crew lived sealed inside a mock spacecraft on the ground, with no real risk to their lives, still documented real strain on mood, sleep patterns, and group cohesion among the volunteers, even with rescue only a door away and full communication with the outside world available at all times. Volunteers who had chosen the experiment, trained for it, and knew precisely when it would end. Actual wintering over expeditions at remote Antarctic research stations, cut off from resupply for months at a stretch by weather rather than distance, have documented similar effects. Irritability, disrupted sleep, and a measurable decline in some cognitive tasks. In trained, carefully selected volunteers who signed up for exactly that experience, both settings, however extreme they feel in the retelling, still allowed for the possibility of extraction if something went catastrophically wrong, even at real cost and real delay, and every participant in both programs knew that possibility existed, which is itself a psychological safety net no outer planet crew would have. None of those analogues include the one variable that would define an actual outer planet mission: the certain knowledge that nothing on Earth can reach you quickly, ever, for years, no matter what goes wrong, and that the light delay alone stretches even a simple question and answer into an exchange spanning hours. Even Mars, at its distance, already breaks real-time conversation with Earth, forcing crews to work through delays of several minutes each way, rather than the near-instant contact every previous space mission has relied on for problem-solving and simple reassurance. Anything farther out breaks it more completely, until the round-trip delay stretches past a full day and communication starts to resemble an exchange of recorded messages more than a conversation at all. Selection and training can filter for resilience, but they cannot manufacture a track record that does not exist. Every method currently used to choose astronauts for long missions is built on data from missions that, however demanding, still occurred within a light minute or two of home, with rescue at least theoretically possible and Earth itself visible as a recognizable object in the sky. Nobody has ever been selected for, trained for, or completed a mission that removes every one of those anchors at once, which means the psychological profile best suited to an outer planet transit is, at this point, an informed guess rather than a proven standard, built by extrapolating traits that helped on shorter, better supported missions and hoping they scale to a situation nobody has ever actually lived through. None of this is presented here to argue that a crew would necessarily fail. Astronauts are among the most rigorously screened, physically prepared people alive, and the countermeasures already in use: daily resistance and cardiovascular exercise, careful nutrition, structured sleep schedules, regular contact with mission psychologists genuinely help measurably on every mission where they have been tried. The point is narrower and harder to dismiss. Genuinely helps and fully solves are different claims, and every one of the numbers in this chapter comes from missions that never had to sustain that help for anywhere near the length of time an outer planet transit would demand. Hibernation, if it ever works, is aimed precisely at this chapter's problem, not the propulsion, not the shielding, but the traveler's mind and metabolism during the long stretches of nothing happening. That is exactly why its current absence matters so much. Without it, and without artificial gravity mature enough to trust with a crew's long-term health, a multi-year mission to anywhere past Mars is not primarily a rocket problem anymore. It is asking a small group of people to remain physically capable and psychologically intact through a duration and a degree of isolation that nothing in the history of human spaceflight has yet tested, on a one-way leg that, for the outer planets, already runs past a decade before any return trip is even seriously considered in mission planning. Put the specific numbers aside, and the shape of the problem is still the same. Every countermeasure medicine currently has. Exercise regimens, dietary adjustments, monitoring protocols was developed and validated for missions measured in months, and every one of them slows rather than stops the underlying deterioration. Slowing a process across 6 months and slowing it across 10 or 15 years are not the same engineering challenge. A countermeasure with a small, tolerable failure rate over a short mission can still fail seriously over a duration long enough, and no dataset currently exists to say at what point in a decade-long transit that failure would become the mission's most urgent problem rather than a background risk to be managed. This is the second-order cost, stacking directly onto the first two. Chapter 3 showed that distance costs years of a life. Chapter 4 showed that those years carry a radiation bill that can exceed a career safety limit in a single trip. This chapter shows that the years themselves, independent of the radiation, independent of the specific propulsion used to get there, degrade the traveler's body and mind in ways medicine does not yet know how to fully prevent, using tools that exist today. Every proposed fix from Chapter 5 reduces one part of this bill. None of them, so far, reduces all three at once, and a mission does not get to solve 2/3 of a survival problem and quietly treat the remaining third as someone else's concern to be figured out later, once the rocket is already built and the crew is already committed. Put every cost from the last 3 chapters onto the same list. Distance measured in years, radiation measured in millisieverts, unresolved medical risk, and fixed technologies still years or decades from maturity. And watch the earlier optimism from Chapter 5 shrink under its own accumulated weight. It helps to hold all 4 categories in view at once for each destination, rather than one at a time, because that is the actual test any real mission would have to pass. Not, is any single obstacle solvable, but are all of them solvable together, on the same timeline, within the same budget. Mars stays on the list of destinations that remain difficult but not structurally closed. The Delta V is demanding but already flown, repeatedly, by robotic missions using proven chemical propulsion. The transit is measured in months rather than years, short enough that current medical countermeasures, however imperfect, have at least been tested across a comparable duration in orbit. Oxygen has already been manufactured in a real experiment from the planet's own atmosphere, and even with a radiation bill that likely exceeds current career limits in a single round trip, no law of physics stands in the way of eventually solving that problem. Only engineering, funding, political will, and an honest reckoning with risk. The kinds of things that can change with enough time and enough sustained institutional attention. That qualifier carries the entire difference between a hard problem and a closed door, and Mars, on the evidence gathered across every chapter so far, sits on the hard problem side of that line. None of this makes a Mars mission close. In calendar time, it remains, by any honest accounting, one of the largest engineering and medical undertakings ever attempted, requiring a level of sustained institutional commitment that has not yet been demonstrated for any project of comparable scope and duration. But large and difficult and not yet funded to completion, describes a great many things humanity has eventually done anyway. Crossing oceans, splitting the atom, mapping a genome, while structurally impossible for reasons unrelated to funding, describes something else entirely. And that is the line this chapter is drawing between Mars and everything past it. A line drawn by the accumulated weight of evidence, not by pessimism about what engineering can eventually achieve given enough time. Everything past Mars starts falling off that list for reasons that layer on top of each other rather than simply replacing one another. A crude Jupiter or Saturn mission, using anything close to current or realistically near-term propulsion, means committing years of transit in each direction. The Delta V climb from Chapter 3 alone roughly doubling and then doubling again past what a Mars mission requires. A radiation bill that dwarfs even Mars's already challenging numbers, and a duration of isolation that pushes well past anything human spaceflight has ever tested. While depending on nuclear propulsion research that, as of this story, has just had its flagship demonstration program cancelled for budgetary reasons, on in situ resource technology that has no equivalent raw material to work with at either destination, and on artificial gravity and hibernation technologies that remain, respectively, unbuilt at the necessary scale and untested anywhere in space. Jupiter compounds the problem further still, with a detail that has nothing to do with transit time at all. The planet is wrapped in an intense radiation belt of its own, generated by its powerful magnetic field trapping and accelerating charged particles to extreme energies, strong enough that even hardened robotic spacecraft are engineered with limited operational lifespans specifically to survive it. and strong enough that a mission built to study Jupiter's most promising icy moon up close has had to be designed from the ground up around heavy, dedicated radiation shielding just to keep its electronics alive for the length of its mission. A hazard layered directly on top of the deep space radiation from Chapter 4. Not a replacement for it, and one that would apply to any human crew lingering in Jupiter's neighborhood with even greater force, since a crewed vehicle cannot simply accept a shortened operational lifespan the way an instrument package can. A human passenger does not get replaced by the next model in the production line the way a failed sensor eventually does. Saturn spares a visiting crew that particular hazard. Its magnetic field and radiation belts are considerably milder than Jupiter's, but grants no relief on transit time, isolation, duration, or any of the propulsion and shielding shortfalls already on the list, which is exactly the kind of partial relief that sounds more encouraging than it actually is once every other requirement still has to be met in full. A mission that clears one obstacle out of 6 has not become 6 times easier. It has simply moved on to whichever obstacle was next in line. Uranus and Neptune push every one of those numbers further still. Transit times, even with the most optimistic near-future propulsion concepts, run past a decade one way on top of a radiation and isolation bill that no current mission design would allow a crew to absorb with an acceptable margin of safety by any standard currently used to certify a human mission for flight. Where a Jupiter or Saturn mission could at least point to serious engineering studies sketching what such a crude voyage might require, no comparably serious human mission architecture has ever been published for either ice giant. Because every prerequisite technology this story has examined, propulsion, shielding, hibernation, would need to mature simultaneously and beyond anything currently demonstrated. And mission planners generally do not spend years designing around technologies that do not yet exist in any tested form, preferring instead to publish concept studies that stop well short of a full mission architecture, precisely because so much of the required technology remains unproven. It is tempting, at this point in the story, to ask whether some intermediate destination might split the difference. A mission that flies out toward Jupiter without attempting to linger, or that targets one of the giant planet's larger moons instead of the planet itself. Neither shortcut removes the core problem. The transit time to reach the outer solar system does not shrink just because the mission plans a shorter stay once it arrives. The years spent getting there and back dominate the radiation and isolation bill, regardless of how long the crew remains once they arrive, which means a shorter stay barely moves the total cost of the mission at all, and a moon orbiting deep inside Jupiter's own radiation belt, whatever relief its solid surface might otherwise offer over the gas giant itself, sits inside one of the most hostile radiation environments in the solar system for exactly the reason described above. Proximity to the very magnetic field generating the hazard in the first place. Line the 4 outer planets up next to Mars, and the contrast sharpens rather than blurs. A Mars mission asks for one open question at a time to be closed: radiation exposure, against a background where distance, medical baseline, and basic resource strategy are already reasonably well understood. A Jupiter or Saturn mission asks for that same radiation question to be closed at a far higher dose, while simultaneously closing questions about propulsion, isolation, duration, and Jupiter's own belts that Mars never raises at all. A Uranus or Neptune mission asks for all of that, at its most extreme values, with no funded technology roadmap currently attempting to close any single piece of it for a human crew specifically. It is worth being precise about what changes between Mars and everywhere past it, because the difference is not merely a matter of degree. Every obstacle in the Mars case has at least one demonstrated working answer somewhere in the historical record. A real mission that flew the distance, a real experiment that made real oxygen, a real, if imperfect, medical baseline from real astronauts who came home. Every obstacle past Mars is still waiting on an answer that has never been demonstrated in the specific environment it would need to work in. Propulsion tested on the ground, but never flown at the scale required, shielding modelled on paper but never built at interplanetary mass budgets. Hibernation studied in animals but never in a human being, let alone in microgravity. Difficult but demonstrated, and difficult and undemonstrated are not the same category of problem. However similar they sound when listed side by side. None of that amounts to impossible in the way a law of physics is impossible. Something more specific and more useful is actually going on. For Mars, the obstacles are the kind that engineering, funding, and time have a real, historically supported chance of closing, because every piece of the puzzle already exists in some working form today. For the outer solar system, the obstacles compound instead of merely adding up. Propulsion that isn't funded, shielding that isn't yet light enough, hibernation that isn't tested, artificial gravity that isn't built, in situ resources that don't exist to exploit, and compounding, still unproven problems do not resolve on the same optimistic timeline as a single hard but known problem with a known solution already sitting on a shelf somewhere. The list of worlds that look almost possible for a human crew does not gently taper off somewhere out past Neptune. On the evidence gathered so far, it mostly ends at Mars. It is worth pausing on why that stopping point lands where it does, rather than somewhere more generous or more restrictive. Jupiter and Saturn are not dismissed here simply for being far. Chapter 3 already showed the delta V and transit time cost of reaching them, without declaring either journey impossible in principle. What actually disqualifies them, at least for now, is that reaching them layers every unresolved cost from every previous chapter on top of an already punishing distance, at once, with no single fix from Chapter 5 currently mature enough to absorb even one of those layers reliably, let alone all of them together. Take away the radiation problem and the trip is still too long for current medical countermeasures. Take away the duration problem and the radiation dose is still unacceptable. There is no single obstacle left standing that, if solved, would make the rest of the problem disappear, which is precisely the compounding signature that distinguishes very hard from not yet possible on any published timeline. Even that narrowed list assumes every remaining planet has a place for a person to eventually stand. And that assumption breaks completely once the destinations themselves are examined, instead of just the journey required to reach them. Everything in the previous 4 chapters was, in a sense, an argument about verbs. This chapter is an argument about nouns. What is actually waiting at the far end of the trip? Physically, regardless of how well the travelling part gets solved, start with the planet next door in the other direction. Venus. It is, by several measures, size, mass, bulk composition, Earth's closest twin in the solar system. And it is also the single most immediately lethal surface for a human being anywhere among the 8 planets. Its surface sits at roughly 460 degrees Celsius, hot enough to soften lead, under an atmospheric pressure close to 92 times Earth's, comparable to the crushing weight found nearly a kilometre beneath the ocean's surface, except delivered by a thick, permanent blanket of carbon dioxide instead of water. 10 Soviet landers reached that surface across a string of missions running from 1970 into the early 1980s, cameras and instruments running for as long as their hardware held out against heat and pressure that had no real analogue anywhere in their testing labs on Earth. One of the later landers, arriving in 1982, managed the longest surface survival of the entire program. Just over 2 hours before the heat and pressure finally won. Others lasted barely more than 20 minutes. Those were machines, purpose-built specifically to survive exactly that environment for as long as engineering could possibly manage. Made of metal and ceramic and hardened electronics designed for nothing else. For Venus, visit does not shrink to orbit only, the way it will for the ice giants a few paragraphs from now. It shrinks to something colder and clearer than that. Engineers have in fact studied exactly this narrower version of a Venus mission. Floating habitats or airships suspended roughly 50 kilometers above the surface, where temperature and pressure briefly resemble something close to Earth's own atmosphere at sea level. Breathable air even becomes a viable lifting gas in the thick carbon dioxide surrounding it, and a human visitor could plausibly work for extended periods without ever descending toward the crushing, scorching world waiting below. American Space Agency engineers gave this exact idea a formal name in their own concept studies, a high-altitude Venus operations concept, envisioning a crewed airship drifting in the temperate cloud deck for weeks at a time, conducting science on the atmosphere and, from a safe altitude, on the planet below. That is what a human visit to Venus would actually look like, if it ever happens at all. Not a landing, but a permanent suspension in the sky, above a surface that will never, under any currently imaginable advance in materials or engineering, host a person who plans on leaving again afterward, and every design study for that airship has had to treat never descend as a hard, permanent constraint rather than a limitation to be engineered around later. Between Venus and the outer giants sits Mars, and briefly, the two worlds this story has already placed in the hard but open category. And it is worth saying plainly why they do not belong in this chapter instead. Both have an actual solid surface, made of the same basic rocky material as Earth's, at a pressure and temperature that, while inhospitable, are survivable inside a suit and a habitat, rather than instantly lethal on contact. Mars's thin atmosphere is inconvenient, not corrosive or crushing. That single distinction, a surface a person could stand on, in principle, inside enough engineering, is exactly what separates a hard problem from a closed one, and it is exactly what Venus and the four giants past it are about to lack, for reasons no habitat design can compensate for. Move outward, past the asteroid belt, to Jupiter and Saturn, and the problem stops being hostility and becomes absence. Both are gas giants, more than 90% hydrogen and helium by mass, wrapped around, in the sense that matters here, essentially nothing solid at all. There is no boundary where atmosphere cleanly ends and ground cleanly begins. Descend far enough and the surrounding gas simply thickens, grows hotter, grows denser, and eventually starts behaving like a liquid deep enough down that pressure alone would crush any vehicle built from known materials long before reaching whatever exotic, metallic state of hydrogen scientists believe exists at the planet's core. Jupiter's atmospheric probe demonstrated exactly what waits down there in practice. It fell into the clouds in December 1995, survived just under an hour of continuous transmission, and was destroyed by pressure and heat at a depth that had barely begun to penetrate the planet's total atmosphere. The single most literal attempt at landing on Jupiter ever made, and one that only a disposable, unmanned probe could have attempted at all. For these two planets, visit was always going to mean flying through the atmosphere, or orbiting above it. Not for humans specifically, but for anything, forever, regardless of how advanced propulsion, shielding, or medicine ever become, because there is nothing beneath the clouds to lower a lander onto, whatever the lander is made of, or however it is powered. Scale reinforces the same point. A storm large enough to swallow Earth several times over has churned in Jupiter's atmosphere for as long as telescopes have been able to resolve it. And Saturn's rings, glimpsed from Earth as a thin, solid-looking band, are in reality a shifting field of countless individual ice and rock fragments, none of them fused into anything resembling ground. Both planets are, in the most literal sense, too large and too gaseous for surface to mean anything more specific than the altitude at which the clouds finally get too thick to see through. Uranus and Neptune share that same fundamental absence, built on a slightly different chemistry. Ice giants rather than gas giants, roughly 80% heavier volatiles like water, ammonia, and methane rather than hydrogen and helium. atmosphere deepening into slush, deepening into something denser and stranger still, with no surface waiting at the bottom for anyone, human or robotic, to touch. Uranus adds a strangeness of its own on top of that absence. Unlike every other planet in the solar system, it rotates almost entirely on its side. Its axis tipped over so far that its poles, rather than its equator, take turns facing the Sun directly across its multi-decade orbit. A reminder that these worlds do not merely lack a surface. They behave in ways that owe nothing to the rocky planet intuitions most people carry into a conversation about landing somewhere. Whatever caused that extreme tilt, most likely some ancient, violent collision early in the solar system's history, it left Uranus with seasons unlike anything a surface-dwelling visitor from Earth could ever have evolved an intuition for. On a planet that offers no surface to stand on and watch them unfold in the first place. Some planetary scientists have modeled conditions deep inside these two ice giants, extreme enough to compress methane into solid carbon, theoretically raining actual diamonds through the planet's interior. A striking illustration of just how far these worlds sit from anything resembling solid, walkable ground. Even setting aside every transit time and radiation number from earlier chapters, even imagining a universe with unlimited propulsion and unlimited funding, a human landing on Uranus or Neptune was never a harder version of landing on Mars, waiting for enough engineering to close the gap. No version of it was ever a landing in any sense that involves a footprint. Consider, once more, what all of this means for the word the previous chapters kept returning to. Possible. A gas giant is not merely a hard place to land, it is a place with no meaningful concept of landed available to apply to it at all. In the same way a cloud offers no floor for a person to stand on, however solid it looks from a distance. Line all four of these worlds up next to each other, and the earlier framing. Engineering problems that money and time might eventually solve, given enough of both, simply does not apply to them the way it applies to Mars. Venus is reachable but not survivable at ground level for any meaningful duration by anything built from materials tested so far or plausibly on any near-term horizon. Its clouds, not its surface, are the only realistic destination. Jupiter, Saturn, Uranus, and Neptune are not survivable at ground level for an even more basic reason. Ground level, in the sense a standing person needs it to exist, is simply not a feature these four planets have. And future engineering, however advanced, does not change what a planet is made of. The spacecraft that visited them never needed to solve that problem, because a flyby or an orbit was always the entire assignment handed to them from the start, and the one true landing achieved in the outer solar system happened on a moon borrowed from Saturn's family. Not on a planet at all. A human visitor, under almost every definition of visit that involves getting out and standing somewhere, would be asking these worlds a question they cannot answer, whatever the surrounding engineering eventually achieves. That is a genuinely different kind of no than the one chapters 3 through 8 were building toward. Distance, radiation, and unproven fixes describe a door that is currently locked but has a mechanism. Something that could, in principle, someday be worked out. A missing surface describes a door that was never installed, because the wall behind it is not a wall at all. There was never a room on the other side for a door to lead into, however carefully the door itself eventually gets engineered. Engineering solves mechanisms. It does not install nouns that were never there to begin with. Every fix examined in chapters 5 and 6 was, in the end, a mechanism-side solution. A better way to get somewhere, survive the trip. Not one of them was ever capable of addressing a noun-side problem, because that was never the kind of problem they were designed to solve in the first place. Redirecting more funding toward them would not change what they are built to do. Return, now, to that machine gliding past Neptune in 1989, closing out a tour that took 12 years and one perfectly timed alignment of planets to complete. Nothing in this story changes what it accomplished. Every planet in this solar system has been reached, photographed, measured, and in several cases landed on or descended into by something built on Earth. That fact was true at the start of this film and remains true at the end of it. What has changed is what visited is allowed to mean once a human traveler, rather than an instrument, is the one asking to go. Walk back through everything that separated those two meanings one more time, in order. A machine only had to survive its own transit and keep functioning. A person has to survive the transit, the arrival, and the return, which is a categorically larger set of demands, not a harder version of the same one. Distance itself, measured honestly in delta V in years rather than kilometers, already turns a probe's patient decade into a human traveler's decade of an irreplaceable life, spent before the mission has asked anything else of them. Radiation turns that same decade into a debt against a safety ceiling that a single Mars trip can already exceed, payable on a schedule no one controls. The fixes that promise to close those gaps: propulsion, shielding, hibernation, artificial gravity, local resources, turned out to be real, funded, and still, every one of them, either unproven at the scale required or one budget cycle away from cancellation. The body itself, independent of any of that funding, keeps returning the same warning every time it is tested. It was never designed for a transit this long, and no countermeasure available today stops the damage, only slows it. And finally, several of the destinations themselves, not the journey toward them, but the worlds waiting at the end of it, simply do not have what a footprint requires, whatever else gets solved first. None of the numbers behind that reclassification came from a single source willing to say what the whole picture implied. That requires assembling mission history, orbital mechanics, radiation biology, spacecraft engineering, and cancelled budget lines into one continuous argument, which is exactly what this film has spent 10 chapters doing. Sort the 8 planets by what the evidence gathered in this film actually supports, and they no longer form a single continuous tour. They separate into distinct categories that hopeful framing cannot merge back together. Mars belongs to the category where the obstacles, real and serious as they are the kind that engineering, funding, and time have historically been able to close. A demanding but already flown Delta V. A radiation bill that exceeds today's official safety limits but not any law of physics. A fledgling but already demonstrated way to manufacture at least some supplies on arrival. And technologies for extending human endurance that remain immature but underactive, if fragile, and politically vulnerable. Development. Mercury sits closer to that same category than to the outer worlds. A genuine rocky surface, survivable in principle with sufficient thermal engineering against its extreme proximity to the Sun, though current mission planning still treats it with far more caution than confidence, and no crude mission concept for it has seriously advanced past early sketches. Its problem, in the terms this film has used throughout, is closer to Mars's than to Venus's. Hard, expensive, thermally brutal, but built on a surface that exists and a set of engineering questions rather than a physically impossible one. Which is exactly the distinction this reclassification is meant to make legible rather than blur. Venus, Jupiter, Saturn, Uranus, and Neptune belong to an entirely different category. Venus is reachable in orbit or in a permanent, suspended presence in its clouds, but categorically, permanently lethal at the surface, for reasons no propulsion breakthrough will ever touch, because the barrier there was never about getting there faster. It was about a place that kills on contact regardless of how it is reached. The 4 giants are reachable only in atmosphere or in orbit, because a surface, in the sense a footprint requires, simply is not part of what any of them are made of, and the single successful landing anywhere in that entire region of the solar system happened on a moon, not a planet. For all 5 of these worlds, no plausible advance in propulsion, shielding, or medicine changes the fundamental answer, because the limiting factor sits at the destination, not the journey. Waiting at the end of any trip, however well-funded or well-engineered that trip eventually becomes. Notice what this reclassification actually does to the 8-planet checklist this story opened with. It does not shrink it to a single word. It sorts it into 3 honest categories instead of one flattering one. Worlds where the remaining obstacles are engineering and funding problems, with a real historical track record of eventually yielding. Worlds where a human presence is possible only in a narrow, permanent, non-landing form, and worlds where no footprint will ever be possible for reasons that have nothing to do with how the trip is funded. That is a less satisfying answer than either "we'll go everywhere eventually" or "we can never leave Earth." It is also the only one the evidence in this film actually supports. None of the 10 chapters between that opening image and this one were arguing that ambition is misplaced, or that the fixes this story examined were not worth pursuing. Nuclear propulsion, radiation shielding, in situ resource production, human torpor. Every one of them is a legitimate, serious response to a real constraint, being pursued by real scientists and engineers for real reasons. What the evidence changes is not whether those efforts matter, but what they can honestly be expected to deliver, and by when and for which worlds specifically. A distinction that gets lost the moment spacecraft already visited every planet is allowed to imply that human visitation is simply the same achievement. Scaled up, that is the shape the opening question was always going to resolve into, once followed all the way through with the evidence actually in hand. Spacecraft already visited every planet was never false. It was simply doing more work than it looked like it was doing at first glance. Quietly letting visited mean orbit for some worlds, landing for others, a single unrepeated flyby for 2 of them, and a lucky touchdown on a borrowed moon for 1 more, all folded comfortably into the same reassuring sentence. Because a machine never has to notice the difference between those outcomes. A human itinerary cannot borrow that same flexibility. A person either survives the arrival or does not. Either finds solid ground to stand on or does not. Either eventually comes home or does not. And for most of the outer solar system, on the evidence gathered here, at least one of those 3 keeps failing. Not because no one has tried hard enough yet, and not for lack of imagination or ambition, but because the worlds themselves were never going to offer what a footprint fundamentally requires. Whichever decade humanity finally works up the funding to try, however many more probes get sent ahead, first to confirm it, somewhere out past the orbit of Pluto now, still transmitting a faint signal back across a gap of light that takes more than a day to cross. That same machine keeps moving outward, carrying a golden record of Earth sounds and images in case anything, someday, catches up to it. It never needed a surface to land on, or air to breathe, or a reason to come home, or anyone waiting for it at the end. It only ever needed to keep going. There is a version of this story that would have been easier to tell and less honest. A straight, escalating line from "we already reached Mercury" to "so eventually we'll stand on Neptune," treating every remaining gap as a matter of time and money, the way public conversation about space exploration often treats it by default. That version flatters the ambition without examining it. The version this film has actually built, chapter by chapter, treats the ambition seriously enough to ask what it would really require, and finds that the honest answer branches. Rather than marching in a straight line to every planet the same machine already touched. Perhaps that is the honest end of this story. Not that humans will never go anywhere else in this solar system, because Mars, at least, remains a door still genuinely open, propped by evidence rather than hope. It is that going and visiting were always going to mean something different for a body than they ever meant for the machine that got there first, and wanting it otherwise does not change what these particular worlds are actually made of. That is a more accurate story than the one the title seemed to promise. Not a smaller one, and accuracy, in the end, is the only kind of promise a film built on evidence gets to make. A promise the machine still moving outward past Neptune never had to make at all, because nothing was ever asked of it beyond arriving. And it did. If there is a single image worth carrying out of this film, it is not a rocket, and it is not a planet. It is the quiet asymmetry between the two travelers this story has followed the whole way through. One still moving outward, unbothered, carrying a record of a species it will never need to explain itself to. The other, still on the ground, working out, planet by planet, chapter by chapter, exactly which parts of that same outward journey a body could ever actually survive making, and being honest enough to let the answer come out uneven rather than forcing it into a single, tidy verdict. Open here, closed there, genuinely uncertain in between. Because that unevenness is what the evidence actually shows, not a failure to reach a cleaner conclusion. The tour is finished. For the machines, for everyone else, it is only just becoming clear which parts of it were ever really an invitation,